So in this one, we are given a matrix 3 by 3, and we're told what one of the eigenvectors is. First of all, we want to show that this really is an eigenvector. And how could you check that? What does it mean to be an eigenvector? Or how would you show that something really is an eigenvector? If we go all the way back to the definition, what does it mean to be an eigenvector of a matrix? Yeah, you got to have this vector, when multiplied by the original matrix, should equal a scalar times that same vector. This is really all it means to be an eigenvector. V is an eigenvector of a matrix if and only if that matrix times the vector happens to be a scalar times the same vector. In other words, the output of A times V, if you think of A as a transformation being applied to this input vector, the output is going to be parallel to the input in the sense that it's just a scalar multiple of the input. And then that scalar lambda is called the eigenvalue. So if we want to verify that this really is an eigenvector, all we need to do is multiply the original matrix A times this vector and verify that the result is just a scalar times that same vector. So let's try this out. Let's try multiplying those together. If we just multiply matrix A times that vector, we can just use our conventional matrix multiplication algorithm, combining rows and columns. So 3 times 1 plus 1 times 1 plus negative 2 times 1, that's just 3 plus 1 minus 2 is 2. Then negative 2 plus 2 plus 2 is also 2. And 0 plus 1 plus 1 is 2. Does that look like a scalar multiple of the original vector? Yeah. In fact, that is, what is the scalar multiplier here? Right, this is just 2 times the original vector. So we've just shown that matrix A times this vector, I'm going to call this V1, is equal to 2 times V1. So 2, that scalar multiplier, is the eigenvalue. The result was just multiplying or combining row and column of the original matrix and the original vector. The usual matrix multiplication operation, you take a row of the first matrix and a column of the second matrix and take their dot product. So for instance, this is 3 times 1 plus 1 times 1 plus negative 2 times 1. That's 3 plus 1 minus 2, which is 4 minus 2, or 2. And then for the second value, for instance, you would combine this row and this column. So you'd have negative 2 times 1, 2 times 1 plus 2 times 1. Negative 2 plus 2 plus 2 is 2. And then lastly, combine the last row and first column. 0 times 1 plus 1 times 1 plus 1 times 1. That's 0 plus 1 plus 1, which is, again, 2. So the result, the output, is just 2 times the input. And that's, again, what it means to be an eigenvector, that the output is a scalar times the original input. Or to put it another way, for purposes of this vector, multiplying by this entire matrix acts like just multiplying by 2. And this is tremendously useful. Being able to treat the entire matrix as just a single number is a huge shortcut. And of course, it only applies to this vector and multiples of this vector also. If we had used like 50, 50, 50, we'd get 100, 100, 100. So any scalar multiple of 1, 1, 1 will also be an eigenvector with eigenvalue 2. So let me make a note of that. One of the eigenvectors is V1 equals 1, 1, 1, and lambda 1 equals 2. That's an eigenvector-eigenvalue pair. And we should be able to find more. We should be able to find another eigenvector with an associated eigenvalue. And since this is 3 by 3, we should ideally be able to find a third one, a third eigenvector-eigenvalue pair. And to do that, what's our usual process for finding eigenvalues? Just from scratch. If you don't have any already, how would you figure out the eigenvalues of some matrix? What's our usual procedure there?
We set the determinant of A minus lambda I equal to 0.
Yeah. We can start by taking the determinant of A minus lambda I and setting that equal to 0. And exactly, we call that the characteristic equation. Whatever you get from the determinant of A minus lambda I, set that equal to 0. That's the characteristic equation, which I think is what part B is asking for anyway. And the reason for that is if you go back to the original definition, AV equals lambda V. If you want to find V or lambda, you would start by subtracting lambda V from both sides. Factor out V from both of these. And if you factor out V, what's left?
A minus lambda.
We got A minus lambda. Although what else do we need here to make that a matrix?
The identity matrix.
You can always put in an extra times I in matrix multiplication. And including that I means we now have a matrix minus a matrix, which actually works. Whereas a matrix minus a scalar doesn't actually make any sense. So we get A minus lambda I times V equals 0. Essentially, we're just trying to find the null space of A minus lambda I. A minus lambda I or lambda I minus A. Ultimately, the order of subtraction doesn't matter here, because if you got two things whose difference is 0, that just means those two things are equal. So you can write it as A minus lambda I or lambda I minus A. Either way works. So in this case, order doesn't really matter. The important thing is, though, since we're effectively trying to find the null space of A minus lambda I, and we already know how to find the null space, you can just augment A minus lambda I with 0 and row reduce. But in order to guarantee we get many solutions, we have to assume the determinant is 0. Because what does that tell you? If the determinant of a matrix is 0, what does that guarantee?
It's not invertible.
Exactly. We want this to be non-invertible. Because if this was invertible, we could just multiply both sides by the inverse and get V equals 0. V equals 0 is the only solution if A minus lambda I is invertible. Because if it is invertible, you could just left multiply both sides by the inverse and get V equals 0. So if we want any non-zero, which we do, we want to find the eigenvectors that aren't just the trivial solution. To get any non-trivial eigenvectors, we need to assume that A minus lambda I is not invertible, which is why we assume its determinant is 0. And we can afford to make this assumption because we haven't specified what lambda is yet. We're essentially just making the assumption that we're going to be using a lambda value that makes this determinant 0. Any questions on the theory behind that so far? And in general, any proof, what does invertible mean? Invertible just means the matrix has an inverse. An inverse in the sense of something that can be multiplied by it to cancel it out. For instance, if you have, let's say you've got some equation, let's just call this M times V equals 0. If M happens to be invertible, that means there's some matrix M inverse that you can multiply, in this case, on both sides. And M inverse times M would be the identity matrix, which effectively cancels out. So you'd end up with V equals, and then anything times the 0 vector would be the 0 vector. In other words, if M has an inverse, then that means the 0 vector is the only vector in the null space. But we want non-zero vectors. We want to find all the eigenvectors, not just the trivial one. So we have to assume that this matrix A minus lambda I is not invertible. So let's try writing that out. If we actually write out A minus lambda I, what would lambda I look like? What are we actually subtracting here?
You would subtract lambda from all the entries on the main diagonal?
Exactly. Lambda I is just lambdas on the main diagonal, so we're subtracting lambda from everything on the main diagonal. So that's going to look like 3 minus lambda, 2 minus lambda, 1 minus lambda, everything on the main diagonal. And then everything else we keep exactly as it is. We take the determinant of that, which means we're going to have to do a 3 by 3 determinant here. So how can we evaluate that determinant? What's some process we could use to write out the determinant of a 3 by 3 matrix?
Cofactor expansion.
Yeah, we could use that cofactor expansion using any row or column as a starting point. What's probably going to be the easiest row or column to use?
In the solution that he posted, he did lambda minus 3.
Oh, yeah, that would that be the lambda I minus a instead of a minus lambda I?
Yeah.
Yeah, so that would be another way to do it. Instead of writing as a minus lambda I like we have here, you could also write it as lambda I minus a.
Okay.
So either one of those works, they'll both give you the same results for lambda, because in both cases, we're assuming the determinant is 0. And if the determinant is 0, then which order you subtract in doesn't matter. You just want to be consistent about it. So either way works, a minus lambda I or lambda I minus a. If we got it written like this, for the cofactor expansion method, we're going to need to take a row or column to use as a foundation. What would probably be the easiest row or column to use here?
The bottom row?
Yeah, probably the bottom row. Because we've got a 0 here. That's a 0 in a matrix if we're finding the determinant. Zeros are basically gifts from the heavens. This 0 is going to make it so much easier to work out everything else. And also this, so I would have used either the first column or the last row because there's a 0 there. And the last row is probably going to make it even easier because there's a 1 there. So I would, yes, definitely use the bottom row here. Any row or column will work, but using the last row is probably going to be easier. So let's try that. We've got 0, 1, 1 minus lambda. So if we write out these cofactors, we've got 0, 0, 1, and 1 minus lambda. And we're going to be multiplying each one of those by a subdeterminant, a smaller determinant, 2 by 2. For example, the 0, we're going to be multiplying that by the determinant of everything not in that row and that column. So ignoring that row, ignoring that column, we've got this 2 by 2 determinant left. But that doesn't really matter because we're going to be multiplying it by 0 anyway. That's just gone because it's being multiplied by 0. And this is a big part of why I would choose a row or column with a 0, because it means that's one entire 2 by 2 determinant that we don't even have to worry about. Meanwhile, the 1 is going to get multiplied by everything that's not in that row or that column. So ignoring the bottom row, ignoring the middle column, we're left with these 4 values. So that's 3 minus lambda, -2, -2, +2. It is the subdeterminant that's going to be multiplied by 1. And then lastly, we've also got a 1 minus lambda. Put that in the next row. That's going to be multiplied by the subdeterminant of everything not in the third row, third column. So 3 minus lambda, 1, -2, 2 minus lambda. Also, the way determinant is defined is going to involve alternating plus, minus, plus, minus, plus, minus. And if you're looking at the first row or first column, you start with plus and then expand outwards from there. Or if you're looking at the second row or second column, you start with minus. Third row or third column, you start with plus. So if you imagine sort of a checkerboard, starting with the plus at the top left and expanding outwards from there, this third row, we're going to start with a plus. So plus, minus, plus. And let's see what that works out to. The 0, again, we can ignore this entire term because it's just multiplied by 0. Minus 1 times, and then this is a 2 by 2 subdeterminant. 2 by 2 determinants you can just multiply across the diagonals and subtract. So 3 minus lambda times 2 minus -2 times -2, which would be +4. And then plus 1 minus lambda times, and then what's left? We've got, again, we can multiply across the diagonal. So 3 minus lambda times 2 minus lambda minus 1 times -2, which is, in other words, going to be +2. Any questions on that setup so far? And let's see what we can get for the rest of it. We've got 3 minus lambda times 2 would be 6 minus 2 lambda minus 4. So the -4 and the 6 combined are just 2. And we're multiplying that whole thing by -1. So that becomes -2 plus 2 lambda. So this entire first cofactor becomes just -2 plus 2 lambda plus 1 minus lambda times this whole thing. And it looks like we've got 3 minus lambda times 2 minus lambda. That's going to be 6 minus 2 lambda minus 3 lambda, so minus 5 lambda. Minus lambda times minus lambda would be plus lambda squared. Plus 2 turns the 6 into an 8. And then we're going to need to multiply that entire quadratic by 1 minus lambda. So we've got 1 times the whole thing plus negative lambda times the whole thing. So minus lambda times 8, minus lambda times minus 5 lambda, and minus lambda times lambda squared. And then we've also got the -2 plus 2 lambda. So it looks like that is our characteristic cubic. And of course, we'll need to simplify that by combining like terms and then hopefully factor it. Any questions on that before we continue simplifying it? And by the way, if you had chosen a different row or column, you'd go through some different steps here, but you'd still get the same overall result. The characteristic polynomial is unique to this matrix. You can't get different results for the characteristic polynomial. You can take different steps to get there, but all rows should lead to that same polynomial. So let's try simplifying this a bit, combining like terms. Looks like we've got a single negative lambda cubed. We've got 5 lambda squared plus another lambda squared. So 5 lambda squared plus lambda squared is 6 lambda squared. And then for the lambda terms, we've got -8 lambda minus 5 lambda. That's -13 lambda so far. Plus 2 lambda, so that's -11 lambda. And then we're left with just 8 and -2, so that's plus 6. And we want that characteristic polynomial to equal 0. So there's our characteristic equation. We've got this entire polynomial from the determinant of a minus lambda I. That needs to equal 0. And by the way, if we had written in this in the other order, if we had written it as negative lambda I minus a, we get the same polynomial, but with it times -1. In the same sense that, for instance, 5 minus 3 and 3 minus 5 are the same absolute value, but exact opposites. In fact, it might be useful to do that. If we just multiply this, both sides of this by -1, we get positive lambda cubed minus 6 lambda squared plus 11 lambda minus 6 equals 0. So we've got this characteristic polynomial. And what do we want to do with that? What's our goal here?
Factor it.
Yeah, ideally we want to factor this. Presumably it's going to factor into 3 binomials, lambda plus or minus something, lambda plus or minus something, lambda plus or minus something, because it is a cubic. And factoring anything larger than a quadratic can get kind of complicated. Usually you have to know one of the factors already or be able to find one of the factors by guessing and checking. However, what do we already know about one of the factors here?
One of them is 2.
Yes, exactly. One of the eigenvalues is 2. We found that from the given eigenvector. So since we already know one of the eigenvalues, we know 2 is a solution. So that means lambda minus 2 has to be one of the factors. In general, if you've got a solution to a quadratic or a polynomial of any degree, then lambda minus that value has to be a factor. And then we just got 2 more factors we need to find. And one way we can do this, now that we know lambda minus 2 is a factor, we can divide it out. We can use polynomial long division to figure out what's left. And there are various ways to do this. One way is by using long division. One other way that I find really useful is the, I don't know if there's a formal term for this, the box method or the generic rectangle method. If you just draw out a rectangle whose side lengths are lambda minus 2 and some unknown quadratic. So we've got something lambda squared plus something lambda plus something. We don't know what those somethings are, but we know that lambda times something lambda squared is going to be something lambda cubed. Negative 2 times something lambda squared is going to be something lambda squared. So we're going to get a bunch of lambda squared terms, lambda cubed terms, lambda terms, and constant terms that better add up to what we want. In fact, we want this to add up to exactly 1 lambda cubed. And also we want the quadratic terms, the lambda squared terms, to add up to negative 6 lambda squared. But there's a couple of different ways you can get a lambda squared here. You can have negative 2 times something lambda squared. That'll get you a lambda squared term. But you can also have lambda times lambda. That will also give you a lambda squared term. So all we know in this case is these 2 terms together have to add up to negative 6 lambda squared. But let's see where we can go from here. We've got lambda times how much lambda squared would multiply to 1 lambda cubed. Yeah, this should just be 1 lambda squared. Lambda times 1 lambda squared equals the 1 lambda cubed we need. But if we have 1 lambda squared, that also gets multiplied by the negative 2 thanks to the distributive property. Lambda squared times negative 2 would be negative 2 lambda squared. Is negative 2 lambda squared what we want? We want negative 6 lambda squared, right? So how much more lambda squared do we need here? Yeah, we're going to need an extra negative 4 lambda squared. That way these terms together add up to the negative 6 lambda squared that we need. So then we just need to ask ourselves, lambda times what would be negative 4 lambda squared? And since we just lambda, negative 4 lambda will work here. So negative 4 lambda is the next term. And of course, if we're using negative 4 lambda, that also gets multiplied by the negative 2 to get what value here? Yeah, we get 8 lambda from the negative 2 times negative 4 lambda. But 8 lambda is what we want. We want 11 lambda. So how much more lambda do we need here? Yeah, we're going to need an extra 3 lambda. To get that, we can just take the lambda multiplied by 3. 3 times lambda gives us 3 lambda. And negative 2 times 3 gives us negative 6, which is exactly the final term we need. So it looks like this multiplication works. The original cubic can be rewritten as lambda minus 2 times this quadratic. Specifically, the quadratic lambda squared minus 4 lambda plus 3. So this is one way to factor out a term. If you have some arbitrarily large degree polynomial and you want to factor out a binomial, this is a great way to do it. Imagine the original polynomial as a rectangle whose side lengths are the factor you know and the factor you don't know. And start filling in values 1 box at a time until you've got the entire polynomial. And then whatever slide length you had to use up here is the other factor. Or alternatively, you could use polynomial long division or synthetic division if you happen to remember that. But any of those methods would work. We just needed some way of factoring the cubic. And now that we've got that, can we factor this quadratic any further? If you aren't given a value at all to start off, there is actually a method of doing this even if you aren't given a value to start with. One way is you could just start guessing, but the problem is there's infinitely many guesses, so you want to narrow it down first. Have you seen the rational roots theorem at all? Does that sound familiar? The rational roots theorem is basically just a way of checking or narrowing down the list of possible guesses. Rational roots theorem. It basically says that if you've got any polynomial with whole number coefficients, then yeah, the P's and Q's exactly. Then you can write a list of all the possible rational roots. If any of the roots are rational, they have to be in the form lambda equals a factor of the very last number, the last constant, over a factor of the first coefficient, which is this one. So if we list those out, what are the factors of 6?
One, 2, 3, 6.
Yeah, so those are the possible numerators, 1, 2, 3, or 6. And the first coefficient is just 1, so that's just 1 as the numerator, or sorry, denominator. So the only possible rational solutions for lambda are 6 over 1, 3 over 1, 2 over 1, 1 over 1, and also the opposites of all those, -6, -3, -2, -1. So we can use the rational roots theorem to narrow it down from infinitely many guesses that we would have to try out to just 8 guesses to try out. So you can just try each one of those, plug it into the original polynomial, see if any of them end up equaling 0. If so, those are going to be roots. The one disadvantage of this is that if the polynomial has any irrational roots, then this one can't find it. But as long as it has at least one rational root, then you can find that rational root, factor it out, and then repeat the process with whatever's left. Or if whatever's left is just a quadratic, you can use the quadratic formula. The only time this really runs into a big problem is if the polynomial has no rational roots at all, if all the roots are irrational or complex. This won't really find complex roots either. But as long as it has no more than 2 irrational roots, because if it only has 2 irrational roots, you end up with a quadratic, and then you can use the quadratic formula. But as long as it has no more than 2 irrational roots, as long as all the rest of the roots are rational, this is a very useful method for factoring any arbitrarily large polynomial. If you want more detail on this, I've got a video that goes into depth on how to use it to factor arbitrarily large polynomials. I'll post that to the Discord afterwards. But let's get back to factoring this one the rest of the way. We factored out a binomial from the original cubic. We're left with a quadratic. Can you factor that quadratic? Yeah, it looks like this factors to lambda minus 3 times lambda minus 1. And then we still got the lambda minus 2 from the beginning. And so since those have to multiply to 0, we now have our other lambda values. Lambda 2 was 2, or sorry, lambda 1 was 2. Looks like the second eigenvalue is positive 3. And the third eigenvalue is positive 1. And the order doesn't really matter. We can label these however we want, as long as you're consistent about it. So just choose a labeling order and stick with it. So we now know all the eigenvalues from that characteristic polynomial. Any other questions on that so far?
After this one, is it possible that you could do the LDU factorization one, number 1?
Yeah, we could try that one next.
Thank you.
And then now that we've got the eigenvalues, if this one wasn't really asking to find the other eigenvectors, but if you did want to find the other eigenvectors, what process could you use to find, for instance, the eigenvector associated with 3?
You'd plug it back into the original matrix.
Yeah, if we go back to the original, specifically the original A minus lambda I, because the last time we saw the eigenvector was in the expression A minus lambda I times V equals 0. So for instance, if you wanted to find V2, the eigenvector associated with the eigenvalue 3, you would write out A minus lambda I. And then actually plug in this eigenvalue for lambda. So you'd be subtracting 3 from everything on the main diagonal. And then since we're trying to solve a system of equations, essentially we're finding the null space of A minus lambda I, you'd augment that with the 0 vector. Simplify, so you just get 0, -1, -2. Row reduce that, and you should end up with infinitely many solutions. But all we really need is a basis for that solution space, a basis for the null space of A minus lambda I. So you should end up with a vector that makes A minus lambda I times that vector equals 0. Isn't it 3 minus 2? Oh, the order of subtraction doesn't really matter. I'm writing this as A minus lambda I. So we're taking the value from A and subtracting the eigenvalue. You can write it in the other order instead if you want. You could write it as lambda I minus A. So this would be, for instance, 3 minus 2, 3 minus 1, and then all these numbers would be flipped also. I usually find it easier to write it as A minus lambda I, because then I can just write out A exactly as it is with no sign changes necessary and subtract lambda from everything on the main diagonal. But ultimately the order doesn't matter, because if you make this lambda minus A or A minus lambda, that's effectively like multiplying both sides by -1, and the 0 vector times -1 is still the 0 vector anyway. So ultimately it doesn't make any difference in this case. And one of the nice things about eigenvectors and eigenvalues is once you've found your solution, you can check it very easily, just like we checked this one being an eigenvector in the first place. Once you find V2, you can check your work by multiplying the original matrix times whatever you get for V2. The result should just be 3 times that same vector V2. Any other questions on that? All right, then let's go back to the beginning of this practice final and try out that LDU decomposition. Wait, 787. Because 789 makes it too easy. Okay, so we've got this matrix A, and our goal here is to factor it. We want to rewrite A as a lower triangular matrix times a diagonal matrix times an upper triangular matrix. And also one of the other requirements for LDU decomposition is that all of the diagonal entries of L and U have to be 1. So we have only 1s on diagonal for U and L. And D, of course, can have any numbers that are necessary on the diagonal. It just can't have any non-zero numbers off the diagonal. And generally for LDU decomposition, the first step you want to do is LDUfactorization. We want to split this up into a purely lower triangular matrix, with zeros above the main diagonal, times a purely upper triangular matrix, with zeros below the main diagonal. And then anything in the other values. So how could we start that? How could we start the LU decomposition first? Is there any way you could modify this matrix to make it just upper triangular? Yeah, we can start with row reducing. We want to get this to row echelon form. Because the U matrix, the upper triangular matrix, really is just the result you get when you row reduce this. Not all the way to RREF, row reduced echelon form, but just to row echelon form. Just to get rid of everything below the pivots. So let's eliminate everything below the pivots to get the U matrix. And we want to keep track of the steps here. What's our first pivot here? Yeah, the one in the top left. Starting with the top row, work your way from left to right. The first non-zero number you're going to encounter is this 1. That's going to count as a pivot. And we want to use that pivot. Yeah, if we write out the corresponding elementary matrix, because we want to keep track of all those as well. So what operation would we do in order to make this happen? Yeah, we want to take row 2 and subtract 4 times row 1. So our first row operation, our first elementary transform matrix is going to have to represent that. Let me call this E1 for the first elementary transform matrix we're using. What would the elementary matrix that corresponds to that operation look like? What multiplier would carry out that operation? And specifically, we put that for where here? Because this is going to look almost like the identity matrix with just that one change, right? For instance, we're not changing the first row, so I'm just going to write the first row of the identity matrix. We're also not changing the third row, so I'm going to write the third row of the identity matrix. But yeah, if we take a look at row 2, column 1, because that's what we're changing. We're changing row 2 by adding the first row, specifically -4 times the first row. So -4, 1, 0. This literally just means take -4 times the first row plus 1 times the second row plus nothing from the third row. So this matrix represents this row operation. And let's see what the next operation would be. And we can kind of combine these into one step, because in our next operation, we also want to use this 1 to cancel out what else? Yeah, we want to get rid of this 7. So let's also subtract 7 times row 1 from row 3. That way we can cancel out both of these in one step. However, I'm still going to write this as a separate transform matrix. E2, we're not changing row 1. We're not currently changing row 2, but we're changing row 3 by subtracting 7 times row 1. So I'm going to write that as -7, 0, 1. Because we're taking -7 times the first row plus nothing from the second row plus the third row exactly as is. That's our new third row. This row is essentially a recipe or a set of instructions for building the new third row. And that's pretty much all we can do with that first pivot. So let's see what this turns into. First row is not changing. Second row, we're subtracting 4 times the first row. So 4 minus 4, 5 minus 8, 6 minus 12. And then third row, we're subtracting 7 times the first row. So 7 minus 7, 8 minus 14, 7 minus 21 would be -14. I think that should work. Any questions on that so far? And then to get it to upper triangular form, we really need only one more step. Because what's our next pivot after the 1 in the first row? Yeah, second row, the first non-zero we encounter is this -3. If we wanted to go all the way to reduced row echelon form, we'd use this -3 to cancel out everything above and below. But since we just need upper triangular form, we just need to cancel out what's below. So let's try this. What could we do to the third row to get rid of this -6? Yeah, we can take row 3 and subtract 2 times row 2. Because that way, -6 minus 2 times -3 would be -6 plus 6. That cancels out. And before we do that, let's write out the corresponding transformation matrix, E3. Again, we're not changing the first or second rows. So I'm going to use the first and second rows from the identity matrix. And then third row, we're taking -2 times row 2, adding it to row 3 exactly as is, and not taking any information from row 1. So 0, -2, 1 means 0 times the first row plus -2 times the second row plus the third row exactly as is our new third row. Again, you can think of this row as a recipe for building the new third row. And let's see what we get as the result. First row is not changing, second row is not changing. Third row, we're taking 0 minus 0 is still 0. -6 minus -6 cancels out. And -14 plus 12 becomes -2. So this is the upper triangular matrix. We've got this in upper triangular form. We've canceled out everything below the main diagonal. So this is what we're going to call U. Except this is not the final U we're going to use. If we were just factoring to LU, I would call this U. But we're going to be modifying this further. I'm going to call this, let's say, U star. Or we already use star to represent complex conjugates. So let's call this U sub 0. This is the starting point, U sub 0. We're going to modify this further to get a better upper triangular matrix. But first, let's find the corresponding lower triangular matrix. Because remember, we want matrix A to be written as lower triangular times upper triangular. We've got the upper triangular matrix. How can we figure out the lower triangular matrix that will make this work?
We just looked at the operations we did, right?
Yeah, because these operations were applied to matrix A to get matrix U. If we reverse those operations, we'll figure out what has to be done to matrix U to turn it back into matrix A. And so, yeah, we'll want to combine those. Because ultimately, we took matrix A, we left multiplied by E1 first, and then E2, and then E3 to get the matrix U. Or let's say U sub 0. So we've got to undo these in reverse order. Left multiply both sides by E3 inverse. Then left multiply both sides by E2 inverse. And then left multiply both sides by E1 inverse. So that means matrix A can be written as this trio of elementary transform matrices in this order, inverted, times U0. And these elementary transform matrices, they're all lower triangular, which means their inverses and products will also be lower triangular. So we just need to invert each of these and multiply them together in this order to get the matrix we're going to call L. Any questions on that so far? And usually inverting a matrix is kind of tedious. But in this case, the fact that they're so simple, they're such elementary matrices, just the one single change makes them very easy to undo. What would be the inverse of, for instance, a matrix that looks like this? What's the only change we need to make? Yeah, we make this +4 instead. Because remember, this matrix represents subtract 4 times row 1 from row 2. The opposite of that would be add 4 times row 1 to row 2 to bring it back to the original. So E1 inverse is going to be the same, but with a reversed sign here. Likewise, E2 inverse, we just change the -7 to +7. E3 inverse, change the -2 to +2. The inverse of an elementary transform matrix is another almost identical elementary transform matrix. You just reverse the sign on the one thing that's not the identity matrix. So we now just need to multiply these together in this order. So let me write that out. We've got E1 inverse times E2 inverse times E3 inverse. And that's going to be the matrix that we call L. And you could just multiply these one pair at a time. I find the easiest way usually, though, is to start from the right and multiply something from the left one at a time. Because remember, these are still elementary transform matrices. For instance, this matrix means keep the first row the same, keep the second row the same, modify the third row by adding 7 times the first row. So let's try that. If this is saying keep the first row of the next matrix the same, keep the second row of the next matrix the same, but modify the third row by adding 7 times the first row. So we take the third row, but we add 7 times the first row. 7 times the first row would be 7, 0, 0. So we add 7, 0, 0 to 0, 2, 1, and we get 7, 2, 1. And of course, you could just multiply this out, row and column combinations. It just takes a lot longer. It's a lot faster if you recognize this is an elementary transform matrix. So all it does to the next one is 7 times the first row added to the third row. Same thing with this one. We've got 1, 0, 0, 4, 1, 0, 0, 0, 1. This matrix is saying keep the first row and third row exactly as they are. So I'm going to keep the first row and the third row exactly as they are, but modify the second row by adding 4 times the first row. So second row plus 4 times the first row would be 4, 1, 0. So it looks like this is our combined elementary transform, or combined lower triangular matrix, combining all of the modifications we made to the original matrix. Any questions on that so far? Then let's put all this together. We now have this matrix we're going to call L. We've got the matrix U. And we can even check our answer here. If you've got time for it and you want to be absolutely sure, you can multiply L times U together and make sure you get back to the original A matrix. Let's take that for granted for now, though. I think we've got everything working out just fine. So we now have our LU factorization. We know that A is equal to L times U. So those are what we have so far. L, and then I'm calling this U sub 0, because we're going to need to make another modification to get what we're going to call U in the end. To do that, though, what we want is L times D times U, where D is purely diagonal, and L and U have only ones on the main diagonal. And note that L already has only ones on the main diagonal because of the method we use to construct it. If you create L and U using this method, you'll always end up with L having ones on the main diagonal, because all we did was add a row to another row. However, matrix U does not have ones exclusively on the main diagonal, so we're going to need to make some modifications. And one way to do that, let me move U over here, because we want to insert a diagonal matrix in between them. Because we want L times a diagonal matrix times U. What's a diagonal matrix you can always insert as a multiplier that doesn't actually change anything? Yeah, we can just fill in the identity matrix. We now have lower triangular times purely diagonal times upper triangular. But that's not quite good enough. If it was this easy, we wouldn't even bother making it a separate category of thing to do. What we want specifically is the upper triangular matrix to have only ones on the diagonals, meaning we've got to have a way to get rid of this -3 and also get rid of this -2. We can do this by factoring out the extra numbers. We can factor out the -3, we can factor out the -2. We just got to be careful about what we do with them. And this 1 I'm not going to worry about because it's just a 1. It's already what we want it to be. But this -3 here, we're going to have to divide by what to turn it into 1? Yeah, we want to divide this by -3. And of course, if we're dividing by -3, you also have to put an 8 times -3 somewhere. So let's take a look at what was influencing this -3. If you consider this diagonal matrix here, which one of these entries actually gets multiplied meaningfully by the -3? What are these, the first one or the second one or the third one?
Second one.
Yeah, the second one here. This one in the middle, that's most strongly influencing the middle row because it's in the middle row of the identity matrix. In fact, if you multiply this out row by column, you got nothing plus 1 times something from the second row plus nothing. Nothing plus 1 times something from the second row plus nothing. Nothing plus 1 times something from the second row plus nothing. So this 1 in the middle is really the key to modifying the middle row. So what we can do is we can divide the entire middle row by -3. As long as we also multiply this by -3. We're essentially doing 2 operations that cancel each other out anyway. Dividing this entire row by -3 and also multiplying this 1 by -3, because this 1 is closely linked to the entire middle row. So let's try that. We're multiplying this 1 in the middle by -3. But since that 1 is multiplied by everything in the entire second row, we need to also divide everything in the entire second row by -3. And let's see what we get there. So -3 divided by -3 is 1. And -6 divided by -3 would be 2. And then if you want to be absolutely certain, you could try multiplying it back out again. Multiply this row by each of these columns. Nothing plus nothing plus nothing, nothing plus -3 times 1 plus nothing, nothing plus -3 times 2 plus nothing. The -3 times 1 gets us back to -3. The -3 times 2 gets us back to -6. So we still get the same result. We're just rearranging where we put the factor of -3. Any questions on that piece so far? And then we can do effectively the same thing with the third row. What do we want to get rid of from the third row? Yeah, we want to get rid of the -2. So we're going to divide the entire third row by -2. But where do we put that -2? Yeah, this last one here. We're going to multiply by -2. So we're dividing by -2 and multiplying something that corresponds to it by -2. Those end up canceling each other out. So we just get -2 here. And then dividing by -2 is just going to turn the -2 into a 1. So now this upper triangular matrix is 1s only on the main diagonal. So this is what we're going to call the actual U matrix we want. And then this matrix is the diagonal matrix. So we've now factored the original matrix into purely lower triangular with 1s on the main diagonals, purely upper triangular with 1s on the main diagonals, and a purely diagonal matrix in between. That's the LDU factorization we're looking for. And one of the big benefits of this is that LDU factorization is unique. There's only one final answer for LDU decomposition of the matrix. For just LU factorization, it's not unique. 2 people working on LU factorization in different ways can get different results. But if they then both also go all the way to LDU factorization, they should both get the same result, which is really handy for consistency. Any other questions on the LDU factorization stuff? Will the diagonal matrix always be? Yes, if all you're doing is pulling out entries from the upper triangular matrix, and those entries just go right here. Just keep in mind, you're not factoring out from just that number, you're factoring it out from the entire row. It's also possible to factor out values from the lower triangular matrix on the left side. But due to the way matrix multiplication works, you'd be factoring something out from a column, not factoring it out from a row. But the way we set this up guarantees that the diagonal entries of the lower triangular matrix will already be 1s. So we generally don't need to worry about that. Any other questions on this factorization so far? Or anything else? What else would you like to work on here? 15 on diagonalization. Yeah. And diagonalization is also largely about eigenvectors and eigenvalues. So okay, so for diagonalization, in order to diagonalize a matrix, the idea is, this is also a factoring thing. We still want to split this matrix up into 3 matrices that multiply to the original. But it's a subtly different way. What we want here, we want A to be split up into 3 matrices multiplied together. The middle one still being purely diagonal, let's say D. But flanked on the left and right, not by lower triangular and upper triangular, but instead flanked on the left and right by some matrix, let's say M, and the inverse of that same matrix on the right. So specifically an invertible matrix and its inverse. So this is our goal. We want A to be rewritten as a purely diagonal matrix, left multiplied by some invertible matrix, and also right multiplied by the inverse of that matrix. And one of the reasons this is tremendously useful, I think this is probably one of the most useful ways of factoring a matrix, is because if you want to multiply A by itself a few times, let's say A cubed, if you actually write out A as MD M inverse each time, what happens when you multiply all those together?
MD cubed inverse of M.
Yeah, all those interior pairs cancel out. M inverse times N cancels out, M inverse times N cancels out. The one on the far left and far right don't cancel out because they're not directly multiplied by each other. They're not adjacent, and you can't just rearrange the order because it's matrix multiplication. But you get M times D cubed times M inverse. And since D is purely diagonal, raising a diagonal matrix to a power is much easier. It ends up just being each entry on the diagonal to that power. So instead of having to multiply a matrix times itself, once you've factored it into MD M inverse format, all you need to do is raise everything in the diagonal matrix to the third power. That's just multiplying numbers by themselves. And then left multiplied by M and right multiplied by M inverse. The tricky part is diagonalizing it in the first place. That part is kind of tedious. But once you've done that, if you diagonalize it the once, then it makes it much easier to raise that matrix to any power you want. In fact, it turns out this even works for non-whole number powers. If you want to, for instance, take the square root of a matrix, you got A to the 1/2 power. That's just going to be M times D to the 1/2 power times M inverse. So this makes it possible to find roots of a matrix, or you can raise a matrix to a negative power. There's even ways you can use this combined with Taylor series to take like e to the power of a matrix or sine of a matrix or cosine of a matrix. Any other questions on that so far? So to actually do this diagonalization, how would you actually find matrix M and matrix D here? What's necessary in order to find those matrices?
Was that the, I might be wrong here, but the GramSchmidt procedure?
Not in this case. GramSchmidt procedure takes some vectors and makes them orthogonal to each other. So that is really useful for QRfactorization. If you want to split into Q, which is purely orthogonal, all the columns perpendicular, and then R, which is just whatever else you need to get back to A.
My bad.
Lambda I. This is all about eigenvalues and eigenvectors. It turns out that this factorization works if and only if the diagonal numbers in D are the eigenvalues of the original matrix. So that's specifically going to be, let's say this is 3 by 3, so presumably there's lambda 1, lambda 2, lambda 3 on the main diagonal. And then matrix M is a matrix whose columns are the corresponding eigenvectors. Let's say V1, V2, V3 as columns. And then M inverse, you just take your eigenvector column matrix and take the inverse of that. But this works ultimately because when you multiply these, when you're combining row and column, lambda 1 ends up getting multiplied by everything from V1. Lambda 2 gets multiplied by all of V2, lambda 3 gets multiplied by all of V3. So you get lambda 1 V1 equaling A times V1. Lambda 2 times V2 equaling A times V2. Lambda 3 times V3 equaling A times V3. So this ends up being the definition of eigenvectors if you simplify it and rearrange the terms of it. But this is generally how you would diagonalize a matrix. You want to diagonalize a matrix, you start by finding all the eigenvalues and corresponding eigenvectors, and then put them together in this format. The one restriction on this, the one thing that makes it diagonalizable versus not diagonalizable, this M matrix has to be invertible. Is there any way you could set up a square matrix whose columns are the eigenvectors and not be invertible? Or what has to be true about the columns to be invertible? Yeah, the columns have to be linearly independent. So for a 3 by 3 matrix, if you can get 3 linearly independent eigenvectors, then that should be invertible. So that means that this matrix can be diagonalized. But if you don't get 3 independent eigenvectors, let's say this matrix only has 2 independent eigenvectors, that means there's no third column. You'd have to repeat the column, which means not diagonalizable. So this is really the key here. In order to be diagonalizable, the matrix has to have as many independent eigenvectors as the width of the matrix. In this case, it's 3 by 3, so you need to have 3 independent eigenvectors. So to check that, let's say we try finding the eigenvectors and see if we have enough. Before we start in the calculations, any questions on the theory behind this so far? All right, let's try this out. We're going to find the eigenvalues using the usual A minus lambda I determinant method to set up the characteristic polynomial. Once we've got the eigenvalues, we can try finding the eigenvectors. And usually this is kind of a long and tedious process for a 3 by 3, but what's going to make it a lot easier with this 3 by 3? What is it about this that looks like it's going to make the determinants really easy? Yeah, we've got all these zeros. Determinants are much easier if there's lots of zeros. And yes, it's also triangular. This is lower triangular, which makes the determinant even easier. So finding the eigenvalues. As before, we're going to take A minus lambda I, or lambda I minus A. Either way works. Take the determinant and set that determinant equal to 0. So that's going to look like minus lambda to everything on the main diagonal and keep everything else as it is. Take the determinant. And we could use the cofactor method or the any of the other methods, but there's a very handy shortcut. If a matrix is purely diagonal or upper triangular or lower triangular, what shortcut can you use for finding the determinant?
Just multiplying like the diagonals.
Yeah, if you just multiply everything on the main diagonal, and I want to emphasize this only works if it is triangular or diagonal. If you've got everything above the diagonal is 0, or everything below the diagonal is 0, then you can just multiply the numbers on the diagonal. So this is a very handy shortcut for finding the determinant of a matrix. Again, only works if you've got upper triangular or lower triangular or diagonal. And of course, you could use any of the other methods as well. You could take the cofactor method, or you can use the shortcut where you're multiplying the other diagonals, like this product plus this product plus this product minus this product minus this product minus this product. So there are various shortcuts that can be used, but this one I think is going to be the fastest one here. We want that determinant to equal 0. And note that this is already in completely factored form. We don't need to, usually we would need to multiply that out, combine like terms, and then factor it again. But there's no extra terms here. This is already factored. So what values of lambda will work here? Yeah, 4 and 7. So let's say lambda 1 is 4, lambda 2 is 7, and that's it. These are the only eigenvalues. And this is kind of unusual because typically for a matrix of this size, how many eigenvalues would you expect? Yeah, we'd expect 3. The 3 by 3 matrix leads to a characteristic cubic. Like if you multiply this out, it would be a cubic, third-degree polynomial. And we usually expect the cubic to have up to 3 solutions. Like if you graph a cubic, you'd expect up to 3 points where it crosses the axis. But in this case, we only get 2, specifically at 4 and at 7. And the fact that 4 shows up twice means it's coming down, just dipping at 4 and bouncing back up, and then going back down through 7. We've got this very special property at 4 that it's not really going through the axis, it's just tapping the axis and bouncing back up. And we can tell that's going on because this term shows up twice. We've got a 4 minus lambda squared. Since that term is being squared, it acts like a quadratic near that point. Whereas this term, 7 minus lambda, is just to the first power, so it acts like a linear function near that point. In general, if you've got some factor to an even power, it's going to bounce off. Some factor to an odd power is going to go through with that root. Any questions on that so far? So, and usually we would describe this as multiplicity. We would say that the eigenvalue 4 has multiplicity 2. Whereas 7 only shows up once in the factored form. So we would say that that has multiplicity 1. And the multiplicities should add up to the size of the matrix. 2 plus 1 is 3 because this is a 3 by 3 matrix leading to a third-degree polynomial. It's just that one of the roots happens to be repeated. So we've got all the eigenvalues. Any questions on that so far? And having a repeated eigenvalue in itself isn't necessarily a problem. Because remember, we want a matrix whose columns are the eigenvectors times a diagonal matrix whose diagonal entries are the eigenvalues. Having a repeated eigenvalue in itself isn't necessarily a problem. Additional significance of multiplicity. Well, if we want to diagonalize this, that 4, we got to have 3 numbers on the diagonal. Let's say one of them is 7. 4 has multiplicity 2, so presumably it would show up twice in the diagonalized form. So we got 4, 4, 7, because 4 shows up twice and 7 shows up once in the factored form. But the problem is we've got to have 3 independent eigenvectors in this. If 4 shows up twice, presumably 4 is going to need to have 2 different eigenvectors. Let's say V1A and V1B. And then presumably the third one would be V2. So we'd have to have an eigenvector associated with 7 as the third column. But in order for this to work, we need to have two distinct linearly independent eigenvectors associated with 4. So this is one of the results that not always, but that sometimes shows up. If you've got an eigenvalue with multiplicity higher than 1, you can expect that that might have a multi-dimensional eigenspace. Like this 7 is going to have an eigenvector and just that one eigenvector and any multiples of it. But if you've got an eigenvalue with multiplicity 2, its eigenvectors might actually form a plane. You might have a two-dimensional eigenspace. Two distinct eigenvectors and any linear combinations of them also count as eigenvectors. So the multiplicity of the eigenvalue in that polynomial tells you the maximum number of dimensions of the space of eigenvectors. But that's a maximum. It doesn't have to be that many dimensions. It's possible that this 4 leads to only one type of eigenvector, which would be a problem, because then we wouldn't have two different columns in this matrix. So that's the big question. Is 4 going to lead to just one eigenvector, or is it going to lead to two independent eigenvectors? Any questions on the theory behind that so far? So let's try that out. Let's find the eigenvectors by plugging in, let's start with 4, because 7 is going to lead to one type of eigenvector. 4 might lead to one or two dimensions worth of eigenvectors. That's really what we care about. So let's try 4. Let's plug in 4 for lambda in A minus lambda I. We'll write out the A matrix exactly as it is. And then we're going to subtract lambda from everything on the main diagonal and augment that with the 0 vector, because we want A minus lambda I times B to equal 0. Again, we're essentially finding the null space of A minus lambda I. But we also know lambda. Let's go ahead and plug in 4 for lambda. And let's see what we get there. Looks like that's going to become 0, 0, 0, 0, 0, 0, 0, 1, 3. So that's our matrix that we want to find the null space of. And we don't even need to row reduce. This is already reduced in the sense that these rows became zeros. So that suggests infinitely many solutions. If we now write out the third row as an equation, let's say we call the eigenvector A, B, C. What would the third row look like as an equation in terms of A, B, and C? Yeah, no A at all plus 1B plus 3C equals 0. So we can treat C as a free variable and B as a fixed variable. Subtract 3C from both sides. So B has to be negative 3C. We can make that substitution. Keep A as a free variable because we don't know anything about A. The A column has no pivot, so A has to be a free variable. B is a fixed variable because there is a pivot in the B column. So we'll replace B with negative 3C. And then C is also a free variable because there's no pivot in the C column. So we'll leave C as it is. Note that we have two free variables, A and C. So we can split this up into a vector with just A plus a vector with just C. So the first number is A plus 0. Second number is 0A plus negative 3C. Third number, no A at all, plus 1C. So that's our solution space. So the set of all solutions to this A minus lambda I times V equals 0 is anything of this format. But we can split this up a little further. For instance, A0, 0, if we factor out A, what's left? 1, and then we still have zeros here. So yeah, that means 1, 0, 0 is an eigenvector. So if we write out eigenvectors here, 1, 0, 0 is an eigenvector. But also we can factor a C out of this one. And then what's left? Yeah, 0, -3, 1. So it turns out that this eigenvalue, which had multiplicity 2, actually does lead to two genuinely linearly independent eigenvectors. So anything in the 1, 0, 0 direction is an eigenvector, because any multiple of that will also work. Anything in the 0, -3, 1 direction is also an eigenvector, because any multiple of that will work. But also all possible linear combinations of them will also work. So this is not just a line of eigenvectors, this is an entire plane of eigenvectors. We've got a two-dimensional eigenspace. And that's good because that means we can fill in one column with 1, 0, 0 and the second column with 0, -3, 1. So because we genuinely do get two different eigenvectors, we can use two columns, both of which match 4 as the eigenvalue. So it looks like this is going to be diagonalizable. And let's put it into a way. We can call these, the usual notation I would use is V1A and V1B. They're both associated with the eigenvalue we're calling lambda 1, but they are two different eigenvectors. So we would have 1, 0, 0 as a column, and then the other eigenvector, 0, -3, 1 as the second column. Any questions on that so far?
When you're finding the eigenvectors, are you writing like the combination how you have like A 0, 0 plus 0, -3C, 1C? I'm kind of confused how you find those. I've been looking at practice problems like that. Is it just because you're writing it in terms of the free variables?
Yeah, very much like how we would find the basis for a null space, for instance.
Okay.
When you reduce the matrix, you turn whatever row or rows remain into equations using the variables in your arbitrary vector.
Okay.
A, B, and C, but whatever variables you want.
Okay, thank you.
Any fixed variables can be replaced with some expression in terms of the free variables, then split that up into a vector for each free variable, factor out the free variable. In this case, we're left with 1, 0, 0 and 0, -3, 1.
Okay, that makes sense. Thank you.
Mm-hmm. So those two vectors in this case form a basis for the eigenspace associated with lambda 1 equals 4. Both of these are eigenvectors, but also all possible linear combinations of them, anything in this format is also an eigenvector. So we've got a two-dimensional subspace of eigenvectors associated with 4. And we should also get, presumably, a one-dimensional subspace of eigenvectors associated with 7. So let's try finding that as well. If we go back to the A minus lambda I, but instead of plugging in 4 for lambda, let's plug in 7 for lambda. That's what we get. We get 4 minus 7, 4 minus 7, and then 0, 1, 7 minus 7. And if we row reduce this matrix, what's going to happen? Yeah, we should only get 2 pivots. Because notice that the third row is just a multiple of the second row. So we can use the second row to cancel out the third row. In fact, what might be useful here is to multiply the first row by -1/3 and also multiply the second row by -1/3. So these just become 1s anyway. So we would get, because we want to turn the pivots into 1s eventually anyway. And then if we subtract the second row from the third row is just going to cancel out entirely. So we're left with 2 pivots. If you now write this in terms of equations, again, let's just call the vector ABC. What would the first row and second row tell you about the values of A, B, and C? Yeah, they're both equal. Well, they're not all equal to 0. Which ones are equal to 0? Yeah, 1A plus nothing equals 0. 1B plus nothing equals 0. And the third row being all zeros doesn't really provide any information. It just tells us 0 equals 0, but we already know that. So A and B have to be 0. So we replace A with 0, we replace B with 0, but there's no restrictions on C. These equations don't tell us any information about the value of C. So C could be anything. C is a free variable. Factor C out of that, and what's left? Yeah, we just get a 1 here, and then these are still zeros. So yes, 0, 0, 1 would be the eigenvector associated with 7. And you could check that as usual. You can multiply the original matrix times this vector, and you should get 0, 0, 7, the original vector times the eigenvalue. And that means we can fill that in for the third column. The third column has to be the eigenvector associated with 7. Whereas the first column and second column are two different eigenvectors associated with 4. Since we've genuinely found 3 distinct eigenvectors, what does that tell you about this matrix? If the columns are linearly independent, what do you know about the matrix? Yeah, this is diagonalizable because the M matrix is invertible. The fact that this matrix has all the columns linearly independent guarantees that it is invertible. So we just multiply by the inverse of this matrix. We call this matrix M or whatever you want to call it. Take the inverse of this, which is guaranteed to be possible, fill that in over here, and you now have A diagonalized. A is equal to a matrix times a purely diagonal matrix times the inverse of that first matrix. And again, the structure for this is the diagonal matrix is eigenvalues on the diagonal with repetitions as needed if one of those has multiplicity more than 1. Like this 4 gets repeated twice, because the 4 had multiplicity 2. And then fill in as the columns of this matrix, the eigenvectors. However, if for whatever reason 4 had led to only one eigenvector, we couldn't have that eigenvector repeated twice because that would be repeated columns, which means this matrix would be non-invertible. So that's what to watch out for. If you have not enough eigenvectors, like if you've got a 3 by 3 matrix, but you only get 2 different eigenvectors instead of 3, that's not enough to fill up the columns with independent vectors, which means that matrix would not be diagonalizable. And that happens sometimes. Sometimes you get a matrix that just cannot be diagonalized because it doesn't have a full set of eigenvectors. But as long as an n by n matrix has n independent eigenvectors, then you can guarantee that it's diagonalizable, even if you've got a repeated eigenvalue. Any other questions on that? Or the general? Yeah. Sorry, yeah.
Sorry. How do you know the order of eigenvectors in matrix M? Like, how do you know which one goes first, second, third?
The order doesn't actually matter as long as you're consistent about it. Like here, I listed 4 first, then 4, 4, 7. So that means the eigenvectors associated with 4 have to go in the first 2 columns.
Oh, okay, I see.
That the order doesn't matter.
Okay, got it.
And then the 7 was listed third, so that means the third column has to be an eigenvector associated with 7.
Okay, got it. Thank you.
And that's changeable. We could have listed this as like 4, 7, 4. We just have to switch the second and third columns. The important thing is that the order of the columns as eigenvectors matches the order of the eigenvalues in the second matrix. If you change the order, that's going to change how this matrix is written, but it'll also change how its inverse is written in ways that end up balancing out. It'll still multiply to the original matrix. So the diagonalization is not truly unique. There are multiple ways of diagonalizing the same matrix. It depends largely on how you choose the eigenvectors. Like you could have said like 5, 0, 0, that's still an eigenvector. And also what order you choose to write them in. So there's many ways to write the diagonalization of the matrix. But again, just make sure you're consistent about order, making sure that the order of the eigenvectors matches the order of the corresponding eigenvalues. Any other questions on diagonalization or eigenvalues?
Could you just summarize real quick again what you did, just so that I remember?
Yeah, just a quick recap of the whole thing. To diagonalize matrix A, we first found its eigenvalues and eigenvectors. So finding the eigenvalues by taking A minus lambda I determinant and set that equal to 0. That turns into a polynomial. You solve that characteristic polynomial to get the eigenvalues. Plug the eigenvalues back into a minus lambda I times b equals 0. Solve that like a null space problem, find the basis of the eigenspace. So as long as you've got as many eigenvectors as the size of the original matrix, that's a full set of eigenvectors. So you can diagonalize it by using the eigenvalues as the diagonal entries of this D matrix, with possible repetitions if one of the eigenvalues has multiple eigenvectors. And then the corresponding eigenvectors as columns in the same order that you listed the eigenvalues. And then you take the inverse of that eigenvector column matrix and put it over here. MD M inverse is the diagonal factorization of the original matrix. And as always, you can check your answer by multiplying it back out. Multiply M times D, then multiply that times M inverse. We should get back to the original matrix A.
Perfect. Thank you.
Any other questions on that? Or anything else you want to work on? We've got 20 minutes left, so that's probably enough for one or maybe two more topics. What else would you like?
Could we go over the QR factorization and the GramSchmidt procedure?
Yeah. Do you have an example of that?
I do not.
Let's just try that for 16. Exercise 16 gives you a 2x2 matrix and says diagonalize it. But let's go ahead and try using the GramSchmidt process and the QR decomposing instead. So let's say we've got this matrix 2, 3, -1, -2, and our goal is to write A as a matrix Q times a matrix R. And what we want here, this is problem, well, it's a modified problem 16. I'm taking the 2x2 matrix from problem 16. The problem 16 says diagonalize this. Instead, we're going to try QR factorization. QR factorization is another way of splitting up a matrix into something times something, specifically with the restriction that Q has orthonormal columns. In other words, we want the columns of Q to be perpendicular to each other in the sense of dot product being 0. And also we want them to all be normalized. We want them to all be unit length. The ortho means all perpendicular to each other. Normal means standardized to length 1. But we want it to contain the same information. We want the column space of Q to still be the same as the column space of the original matrix. We don't want to lose any information. And this is really what the GramSchmidt process is all about. The GramSchmidt process takes a set of vectors that are not perpendicular and modifies them so they are perpendicular but still span the same space. In this case, the same plane, because we've got 2 of them, so we'll get a 2-dimensional subspace. And then R is basically just whatever extra is necessary to make Q times R get back to the original matrix A. And one way of finding R is to just multiply both sides by Q inverse to solve for R. Let's try this out though. The GramSchmidt process involves taking the original vectors, in this case, the columns. Let's just call those U1 and U2. So U1 is 2, -1. And U2 is 3, -2. So those are 2 vectors. They're linearly independent. So the 2 of them together are going to span a plane. What we want to do is take those 2 vectors and modify them so they're perpendicular, but still span the same plane. And this is what the GramSchmidt process is all about. Turning a set of vectors into orthogonal, but still keeping the same overall information. Still keeping the same span. So the GramSchmidt process. For orthogonalizing vectors. The idea is we're going to make 2 new vectors. In this case, we usually call them V1 and V2. And what we're going to do, we're going to go one at a time, taking a vector from the original set, and then taking off anything that's not already perpendicular to what we have so far. The first vector, U1, we can just keep exactly as is. The GramSchmidt process usually starts with just taking one of the vectors to start with as a foundation and keeping it exactly the way it is. So we're just going to keep 2, -1 exactly as is. But then the second vector, we're going to take vector 2, vector U2, and modify it. Specifically, we're going to strip off anything that's not already perpendicular. And the reason we need to do this, if you've got, let's say, vector U1, which we're calling V1 now, is 2, -1. So that's V1. The vector U2 is 3, -2. Something like this, maybe. Let me see if we can go further. The problem is U2 is not perpendicular to V1. So we're going to modify it so it is. Specifically, we're going to take U2 and imagine splitting it up into a parallel component and a perpendicular component. U2 perpendicular and U2 parallel. So this is just like splitting a vector into XY components, except instead of using the usual XY axes, we're tilting the axis. So we get a parallel component and a perpendicular component. And you could think of this as a vector addition thing. You could say U2 parallel plus U2 perpendicular. You can think of those as vectors in their own right. The parallel component plus the perpendicular component is the vector itself. But what's the only piece of this we actually want to keep for V2? Which component?
The perpendicular component.
We want the perpendicular
noodles.
So we can get that by subtracting the parallel. U2 perpendicular is U2 minus the parallel component. By subtracting the parallel component from both sides, we're getting rid of the parallel component, so all that's left is perpendicular. So we can write V2 as U2, because V2 is the perpendicular component we seek. We take U2 and we subtract U2 parallel. But what do we call the parallel component? What do we call it if you take a vector and flatten it onto the direction of another vector?
The projection.
The projection. Specifically, the projection of U2 onto the V1 direction. By subtracting the projection of U2 onto the V1 direction, we're getting rid of everything in the V1 direction, so all that's left is guaranteed to be perpendicular to V1. So that's the projection we're getting rid of. All that's left is the perpendicular component. So that's really the geometric scheme here. We're getting rid of everything that's not perpendicular so that all that's left is perpendicular. And there are various ways you can calculate the projection. I think probably the easiest one to use in this case, since we're just projecting a vector onto one other vector, is the dot product approach. We take some fraction times V1 because we want to get rid of something in the V1 direction. And that fraction is going to be U2 dot V1 over V1 dot itself. So input dot target over target dot itself times the target direction. So let's see if we can calculate that. We got U2 exactly as it is. We're modifying it by subtracting a fraction times V1. And for that fraction, we just need to take some dot products. For instance, U2 dot V1, that's 3 -2 dot 2 -1. And what is that dot product? We've got 6 plus 2, so yeah, that looks like 8. Divided by, and then the denominator V1 dot itself. So V1 dot itself, that's going to look like what? Yeah, that'll just be 5. So if we subtract these, we've got 3 minus 16/5. 3 is the same as 15/5. So that'll be -1/5. And then -2 minus -8/5. So -2 plus 8/5. That's the same as -10/5 plus 8/5. So that's just +2/5. Or no, -2/5. Yeah. And also one thing to keep in mind is that the magnitude of the vector doesn't matter. All we care about is direction. So we can multiply or divide this by any scalar and it'll keep the same direction. In particular, I don't want to have to deal with these fifths. So I'm just going to multiply this by -5 and get 1, 2. That keeps the directionality we need. I mean, it flips it to the exact opposite direction, but it's still spanning the same line. And it gets rid of the inconvenient fractions. So let's say V1 is 2, -1, and V2 is 1, 2. Or you could keep the -1/5, -2/5. I think it's just going to be easier to work with whole numbers here. So that's our V1 and V2. V1 is 2, -1. V2 is 1, 2. And it keeps the same overall information. The span of these two vectors is the same as the span of these two vectors. But what happens when you take the dot product of V1 and V2? V1 dot V2 is going to equal what here? Yeah, it's 0. 2 times 1 plus -1 times 2. V1 dot V2 is 0. And what does that tell you about these vectors geometrically?
They're perpendicular to each other.
Exactly. We've taken the two vectors that were not perpendicular and modified them so that the new vectors are perpendicular, but still contain overall the same information in terms of spanning the same column space. So we've orthogonalized. That's the whole point of the GramSchmidt process, to take vectors that are not perpendicular and modify them so that the results are perpendicular. There's one more thing we need to do to get to matrix Q, though. The requirement for matrix Q is that the columns be orthonormal, which means orthogonal, like these ones already are, but also normalized. And this is where we do need to care about magnitude. How do you normalize a vector?
You take its magnitude and you divide the vector by its magnitude.
Right.
So the square root of the square root of the or I guess in this case it'd be 1 over the square root of the two components squared, each added.
In general, we want let's say vectors Q, and we usually call this Q1 and Q2. So U1 and U2 are the original vectors. This is just the usual. V1 and V2 are modified so that they're orthogonal. And then Q1 and Q2 are the same directions as V1 and V2, still orthogonal, but modified to be unit length. We want these to be length 1. Unit length. And yeah, the easy way to do that is to just take each vector's magnitude and divide the vector by its own magnitude. So we would say, let Q1 equal V1 divided by its own magnitude. And let Q2 equal vector V2 divided by its own magnitude. And for magnitude, you can use the Pythagorean theorem, essentially, the Euclidean distance algorithm. You could also think of it as the square root of a dot product. The magnitude of a vector is defined as the square root of the vector dot itself. So you can always rewrite magnitudes in terms of square root of a dot product with itself. So let's try that. If we just calculate each of these magnitudes, magnitude of V1, what would be the magnitude of 2, -1?
Square root of 5.
2 times 2 plus -1 is 5. So square root of 5. And likewise, magnitude of V2 looks like that's also going to be square root. So all we need to do is take each vector and divide by its own magnitude. So that gives us Q1 is 2, -1 divided by square root of 5. So 2 over square root of 5, -1 over square root of 5. And then Q2 is vector V2 divided by square root of 5. So 1 over square root of 5, 2 over square root of 5. And this gives us new vectors that are still perpendicular to each other. The dot product of these two vectors is still 0, but they now have the even more useful property that they're both unit linked. And one of the really convenient things about this is that all the dot products become very predictable. Q1 dot Q2 is 0 because they're orthogonal. Q1 dot itself is 1 because it's unit linked. Q2 dot itself is also 1 because it's unit linked. So all the dot products become 0s and 1s. And we use these Q vectors to make what we call the Q matrix, capital Q. Matrix, capital Q, is just going to be vectors Q1 and Q2 as columns. And of course, there could be more. If A was 3 by 3, we'd get 3 vectors, Q1, Q2, Q3, so those would be the columns. So in this case, matrix Q would be, and we just list these out, 2 over root 5, -1 over root 5, and then this column, 1 over root 5, and 2 over root 5. So this has, among other properties, the property that its columns are orthonormal to each other. Unfortunately, the usual terminology is that this is called an orthogonal matrix. If we describe the matrix as orthogonal, that tends to mean its columns are orthonormal. Personally, I think we should be calling this an orthonormal matrix, but the usual terminology seems to be just to call it an orthogonal matrix. But one of the really handy properties of this is that when you take its transpose, if you transpose this, what happens to columns of a transpose? When you take the transpose, the columns turn into
rows.
Yeah, columns turn into rows. So if you multiply Q transpose times Q, Q transpose has Q1 and Q2 as rows. And then Q has Q1 and Q2 as columns. So if you were to multiply these together, you'd be combining row and column. And the combination is essentially a dot product. If you take Q1 dot itself, what should you get? If it's an orthonormal, if it's orthonormal, it's normalized, so that means its magnitude is 1. Generally, Q1 dot itself is going to be the magnitude squared, but the magnitude is 1 because we normalized it. Likewise, Q2 dot itself is also going to be 1. But what about the mismatched pairs? What's Q1 dot Q2 going to be? 0.
0.
And likewise, Q2 dot Q1, also 0. And what do we now have? Yeah.
Identity matrix, yeah.
So if we have a matrix times something equals the identity matrix, what do we typically call that? If you multiply a matrix times something and it cancels it out to get the identity matrix. Yeah, the inverse. Q transpose is Q inverse. This is one of the really important properties of any orthonormal matrix. If you've got a matrix whose columns are orthonormal, assuming it's a square matrix, a square matrix whose columns are orthonormal has this property that the transpose of the matrix is the same as the inverse of the matrix. So that makes finding the inverse really easy. You don't have to go through all the process of like augment with the identity matrix and row reduce. All you've got to do is transpose it. Swap the rows to columns and columns to rows, and you've got the inverse. And this only works if the matrix has orthonormal columns. Symmetric matrices to be diagonalized with Q. I'm not sure. There's probably a mention of that in the textbook in, what is it, section 6 point something, 5 point something, properties of symmetric matrices. Yeah, if you take a look, let me check where that is. Yeah, section 6.4 in the textbook has a whole bunch of properties of symmetric matrices. So it's probably listed in there somewhere. But yeah, generally this is the QRfactorization. I guess that's really good. But yeah, the orthonormal matrices have various really useful properties. As I think cubing the diagonal matrix is just a different use of the same variable. The problem is we've only got so many variables, so some of them get reused. But any diagonal matrix is going to be orthogonal anyway, because any single column with just one number in it is going to be orthogonal to a column with only one other number in it. But I think that's just a different use of Q in the different context. But once you've got Q, again, for QR decomposition, the idea is to rewrite A as Q times R. We want A equals Q times R. So we've got Q from using the GramSchmidt process and normalizing. How could we find R?
By multiplying A by Q inverse or A transpose.
Exactly. We can just multiply both sides by Q inverse, and because Q inverse happens to be transpose, we can just left multiply both sides by Q transpose. Q transpose is Q inverse by definition, so those are going to cancel out. And R is going to be Q transpose A. So once you find the Q matrix, you can just transpose it, multiply by the original matrix A, and that gives you the R matrix. You now got the Q matrix you found through the GramSchmidt process. You've got the R matrix you found by multiplying Q transpose times A. And you now have a purely orthonormal matrix and another matrix you can multiply it by to get back to the original. So that is QRfactorization, splitting A up into purely orthonormal matrix Q times something else. Any other questions on
that? I had one more question, Casey. Sorry. When it comes to the GramSchmidt process, do you just keep on when it gets larger, like say for V3, the third like the third column of the Q, do you just increase? Do you just like keep on subtracting it by the previous vectors projection?
Yeah, you just keep subtracting the projection onto, like for V3, you take U3 and subtract the projection onto the V1 vector you found earlier, and also subtract the projection of U3 onto the V2 vector you found earlier.
So would you subtract the projection of U1 on the projection of U2 as well in V3?
Well, V3, for instance, would be based entirely on so V3 would be defined as U3 minus the projection of U3 onto the V1 direction you already found, also minus the projection of the same U3 onto the V2 direction you already found. So you're just taking U3 and subtracting projections of U3 itself onto all the vectors you've already found. And then V4, same idea. You start with U4 minus the projection of U4 onto V1 and V2 and V3 independently. All right, I've got to get going, but good luck on the rest of your finals. Have a good summer, and I hope to see you in Math 22B.
Thank you.
You're welcome.